Hi everyone. Yep, my name is Joanne Cheng. So I work for Keen.io, where I work on a lot of front-end interfaces for users who want to analyze data that they collect on our service. So I do work a little bit with data visualization, and I'm always looking for new technologies to help us visualize data better on the browser. So there's my Twitter account. If any of you want to heckle me or correct me or ask any questions during the talk and you don't feel comfortable tweeting at the hashtag for some reason, you can go direct message me or tweet at me during the talk at any time. So I am here to talk to you today about getting started with WebGL. Talking to many other JavaScript developers about WebGL, I've heard several different opinions. Some say it's intimidating, some say it's mysterious, and most very intelligent web developers I know don't ever really work with WebGL because they just don't have a use for it. Because many of us don't really include 3D in our everyday web applications. And that's kind of what I thought too before diving into it. But WebGL isn't just for 3D graphics. It is often used for 3D graphics, but it's really just, it describes a set of native JavaScript API calls used to render any type of graphics, 2D or 3D, on your computer's GPU or graphics processing unit. The JavaScript API calls are based off a version of OpenGL ES, which is a smaller subset of the OpenGL APIs that you probably have on your laptops or your computers. So there's a lot of advantages for rendering graphics on this GPU versus the CPU. I like to think of this analogy with guinea pigs. So when you're rendering graphics with the GPU and you have to do a simple task like figure out what color a pixel needs to be, you're running on a single thread on the CPU, and while you can calculate it very quickly, because laptops these days and monitors usually have a lot more pixels, it might take a while. But with the GPU, we can do all these calculations for all the pixels at once, and it's designed for that. And this is pretty handy if you think about the Retina displays. And so while we're using JavaScript to work with WebGL, we actually talk to the GPU using another language called GLSL with something called shaders, but I'll explain that more later. So WebGL has been supported by several mainstream browsers for the past few years, mostly just Chrome and Firefox, but there's tons of examples. And there's tons of examples out there of WebGL used frequently for games and experimental browser art, like what you see here right now. However, WebGL support has increased a lot in the past few years, and now you're seeing a lot of uses of WebGL outside of experimental art and games. So WebGL is now supported by almost all current browsers, including mobile browsers. And because WebGL 2.0 has recently been released, this allows for higher precision in shaders, which means you'll see clear graphics on your screens. With this amount of support, there's now a lot of really interesting and maybe what some people would call practical projects made with WebGL, and I'm hoping to give a very broad overview of some of the tools to work with WebGL, some of the projects that are already out there, some concepts, and just help you demystify this technology. So I work a lot in data visualizations, and 3D graphs are usually like a huge no. Like they're really hard to read, and they're kind of tacky, and like they can be kind of terrible or just like confusing. If you ever want to just look at really bad 3D graphs, you can go to WTFviz.com. But I've sort of been intrigued by the idea of practical 3D visualizations after seeing this graph that the New York Times released. So last year, New York Times released this interactive 3D chart that used 3D to its advantage. What you're seeing right now is a yield curve, which is a graph that shows how much it costs the federal government to borrow money for a set of time. And it shows the changes of that value over the past 20 or so, or 15 or so years. It also has a set of particular views. Users can interact with it and zoom in and out and click around, but the particular views kind of hide the other axis of data, so you're only looking at two at once. And you can zoom in, and every time you look at a new view, I think you learn something new, and it kind of tells a different story. So I kind of wanted to recreate this chart with a different set of data that I'm really passionate about. And since the WebGL API can be kind of confusing to get started with, I want to just start visualizing something right away. And I used a library called 3JS, which Rachel mentioned in her talk. So 3JS is a popular WebGL wrapper that obscures a lot of the complexities of WebGL. So I really love data sets from nature. I love seeing patterns emerge from weather and earthquakes and other, I guess, disasters. So this is just this is a graph of the time where tornadoes occur in the US. And so this was produced by NOAA. NOAA has an entire page full of just graphs and CSV files of tornado data from the past few years and really interesting visualizations. So I kind of wanted to jump on like the visualizing tornadoes bandwagon. So I decided to try to recreate that, do something similar to that yield curve graph, but look at tornado occurrences by hours. And I also wanted to look at different views. So what did the data look like over a month? What did it look like for a single state? And this is just the first version of the chart I created. What you're seeing here is just the data for Texas for the month of May. And the peaks you see, I think, are around like 4 or 5 o'clock, where tornadoes occur the most. And I also thought this was the most pretty looking data set, so this is what we're working with. But I just want to show you some of the important parts of the code to get started with 3JS. I guess I'm blocking some of the code. So with 3, we need to set up a scene, a camera, and a renderer before we can actually draw any objects. A scene is a container for all the shapes that you draw, and it also contains all the lights in your scene. And once we initiate it, we can add lights and shapes to the shape objects to the scene later after we create them. A camera describes how the objects in the scene will be viewed. We're using a perspective camera, which means things that are further away from the camera will be displayed smaller. And it's kind of what the camera, kind of a diagram of what's going on in the camera. So there's 4 arguments that the camera takes. The first one is called vertical field of view, which is how much the camera can see vertically in degrees. The horizontal field of view, which is kind of defined in that middle in the diagram, it's calculated from the vertical field of view and other parameters. Second parameter is the aspect ratio, which is just the width over the height. And since we kind of want a normal looking graph, we're just going to keep that calculation pretty simple. The last 2 parameters are the near and the far plane. They describe the area in front of the camera where objects can be visible, and if an object position falls outside of those 2 variables, then it won't be visible from the camera. And once the camera is initiated, we're also free to move it around the world. And here I'm just moving the camera Z position 10 units, which just moves it closer to us by 10 units. So this is kind of the coordinate system we're working with. The last thing we're initiating is the renderer. It's the WebGL context. Here we're only passing the canvas HTML element where this is all going to be displayed. We also call other methods afterwards to set the size of the canvas, and we also set the background color, which is just the same background color as a screen. And the last line will actually draw the scene, which will contain all the shapes, and draw the scene according to the camera properties. Unfortunately, we just get this right now. So we need to start adding shape objects to our scene. So to draw this main graph object, I use what's called a plane geometry in 3JS. And this is what a plane geometry looks like without, in its very basic form. It's just a flat rectangle, but we'll be changing the heights and the colors later. So there's also several other geometries that the 3JS provides: box, sphere, ring, and also custom shapes. And these are all helper functions to help us create 3D shapes quickly. The first line that we create is defines a material and that the shape will be made of and what it'll look like. We're using a basic material which just simply displays the color that we pass in. If we pass in the wireframe attribute, we can take we can see each individual vertex. The geometry describes a shape that the object will take. This is the plane geometry object that I was talking about. We pass in the width, the height, and the number of segments across and vertically to the plane geometry. And so those triangles that we saw were actually the segments. The mesh combines the geometry and material together to form the object that we see. So we need to also add that object into the scene. And also, just to note, render.render is called after this code snippet. To actually visualize the data and map the data to different peaks, I actually used D3 scales to help me map that. So I'm really relieved that the last talk was about D3. So just a reminder that height scale just returns a function that takes a value and maps it to the range that you see there. So after that, I just iterated through all the vertices and changed the Z attribute to the correct height. And then we could also change the color of each vertex. And I once again used D3 to help me map the values of each face of each vertex to a color between light blue and darker blue. And so all that code lives in an example on GitHub. So there's a lot of advantages to using Three.js. It did take a good amount of code to get started, but compared to WebGL, it's much less. It's a pretty consistent and easy to understand API, and there's a huge community of users. There's several example projects online. But the disadvantage is that it's not too well documented. The documentation on the entire site contains a really fantastic tutorial to create a rotating cube, the one that you see here. And then you're kind of on your own, just Googling for help and desperately searching GitHub for examples, or digging through the source, which is a little hard to read because the original WebGL APIs are so complex. So I found it pretty difficult to get started, and I learned mostly from digging through examples on GitHub. So if you ever want to dig into Three.js, that's probably a really great way to go about it. So I'm going to shift completely away from Three.js into something that might be into a library that already exists. So WebGL is currently being used by Mapbox in this library called Mapbox.gl. It renders maps with WebGL instead of tiled graphics. That way, maps render at a super high frame rate, and you don't have to wait for images to load every time you zoom into a new zoom level. You can see that zooming in and out is a pretty fast process in this GIF. And using WebGL also allows for maps to be rotated and tilted, as you can see, and still be displayed at a good quality, something that's a little harder for image-based maps to do. Something that I sort of recently fell in love with is this library called WebGL that Uber just released, which is built upon other really commonly used tools, both internal to their team and external libraries. WebGL is a combination of React, Mapbox.gl.js, which we just saw, and another WebGL wrapper called Philo.gl, which is a much lower level WebGL wrapper. That library is also now end of life, but it has a large number of examples that are still up that are really fun to go through. So what WebGL does is it draws a WebGL layer on top of a map layer and uses React as kind of glue to handle interactions and make sure that the WebGL layer, all the points are in the right spot. And so you can create really interesting visualizations. This example is from Uber's site in a really cool blog post they released about how they use WebGL. So using this stack of technologies, you can create really powerful interactive visualizations like the one you see here that really would be way too intensive for SVG, which is more commonly used to plot things on maps. So I decided to play around with WebGL with some of my favorite data sets, which is earthquakes. This one you see here is just earthquakes from the last week. And I used their scatter plot layer, which lets me plot earthquake latitude and longitude on a canvas layer on top of the map layer. And so, like I mentioned before, all these layers are wrapped in React components, so the position of the dots can be updated whenever a user interacts with the map. So this is kind of a rough approximation of what the code looks like. If you're familiar with React, you'll notice that everything's wrapped in components. Nothing here is WebGL specific or Mapbox.js specific. All that's been abstracted away in React components. So we're just getting the longitude and latitude of each earthquake and passing into the scatter plot layer. But the problem is I want the magnitude of the earthquakes to be reflected in the size of each circle, and I can't do that, so I had to do a little bit of hacking. So that kind of leads to the next topic. How do we turn a JavaScript array of numbers into pixels on the screen? So after we initiate a WebGL context, there's two other really important steps we need to send code and data to the GPU. The first step is creating shaders, and the second step is sending the data in buffer objects for the shaders to process. So what are shaders? There's two types of shaders that each WebGL program has. A vertex shader retrieves a collection of vertices, and the shader gets executed once for each vertex in the collection. This is where all the points get translated into pixel values. This is also, in that earthquake example, this is where the latitude and longitude of each of those earthquakes gets translated into canvas values. And a fragment shader gets executed afterwards for each pixel. And it returns a color for each pixel rendered by the vertex shader. So every WebGL program has one vertex shader and one fragment shader. The native WebGL API requires you to pass these programs in as strings, which can be kind of cumbersome and hard to manage, but there's a lot of tools out there to help you create and manage shaders. So I'm also a huge fan of throwing myself deep into code until I figure stuff out. And so I just want to show a little bit of vertex shader code and how it maps to JavaScript objects. So I apologize if this is confusing. I'm a little scared. So when we send vertices when we send points and data for the GPU to process, we have to be really specific about what we send. So this is a very reduced version of what's happening in JavaScript and the vertex shader. On the JavaScript side on the left, we're taking that array of positions, so an array of objects, and turning it into a flat array, or a flat array of floats. We call some WebGL functions, just magic right now, and that we can access those points in a vector 3 of positions. So so we can access, for each of those positions, we can access the X, Y, and Z using X, Y, and Z in the shader side. So this is it's kind of magic right now, but if we look back at the map, we can see all the radius of the points are the same. And that's being set where that yellow box is highlighting in the vertex shader. So if we want to send the magnitude, we have to do a couple of changes. So I'm adding in a fourth attribute to that position called magnitude. And instead of passing or setting a vector 3 of positions, it's now a vector 4. And we access that fourth attribute of the position using just calling positions.w. And that way, we're able to map the magnitude to each each dot that we see. Some other examples of things we can do in the shader to make this graph a little better is changing the radius size depending on the zoom level. So I did that using shaders by passing in the zoom as something called a uniform. This is just a comparison of what they look like. So there's a function in the JavaScript code in WebGL that updates the uniforms of the WebGL program every time a map state gets updated. So it's viewport or it's zoom level, and this is all, it gets updated thanks to React. A uniform is kind of like an attribute, but the difference is attribute variables vary from vertex to vertex in a shader. So positions are different for every point that we send in, but a uniform is the same for every vertex. So the zoom level will be the same for every position in that shader. So, and also you'll notice a smooth step function. That's just a function that normalizes the zoom value, which is between like 1 and 19 or 1 and 20, to a value between 0 and 1. And it just prevents the map from looking like this, which is just hard to read. So what I really love about WebGL is that it comes with so many common useful libraries out of the box. Things like React and Mapbox.gl are really well supported, and there's tons of documentation out there. But it also lets you seamlessly integrate with shaders. So it combines high-level libraries with low-level shaders with a lot of the complicated steps already figured out. But I really love playing around with shaders because they're honestly so cool. They're able to let you manipulate what you see pixel by pixel just by using math, which I never thought I'd understand, but it was, once you dig around with it, you become a lot more comfortable. So there's a lot of things I didn't cover today. Rotations, animations, moving things around in WebGL, rendering 3D files exported from modeling tools such as Maya, more advanced shaders, how to interact with objects you see using JavaScript callbacks and events. But despite that, there's still a lot that can be done with just a few things the best way to learn about this stuff, I learned, is to just really get messy. And I'm going to upload these slides later if you want to look at more resources and data sets. When you're working with a high-level library such as 3JS or diving into the low levels of WebGL, this type of programming can be uncomfortable because it's so different from day-to-day web development, and you'll probably make really interesting mistakes. But this technology is becoming more and more popular because it's so well supported by browsers. And with libraries such as Mapbox.gl, you may already be interacting with WebGL projects and not knowing about it. And it's a really fun and useful skill to add to your toolbox. Thank you.
That was a really awesome introduction, and your demos were really awesome and cool. I really like the fact that there's been this big boom in 3D interaction in the browser. I mentioned before I come with a Java background, and OpenGL has been around for 20-something years, but WebGL, which I think is based on a subset of OpenGL ES, is fairly new. I think it's from 2011-ish.
I think, yeah, Chrome and Firefox might have been supporting it a little bit earlier than that, but I think IE support is really, really new, and mobile support is also pretty new.
Yeah, I was wondering if, and I've done a lot of 2D graphics kind of stuff, and I've heard that people have been using WebGL for I guess progressive enhancement that falls back to Canvas. And as someone who doesn't get to do many graphics in their job, and one thing I'm always focusing on is how to test things. Do you know any testing libraries that are being used, or is that not a thing people are doing quite yet?
That's actually, it's a really hard, testing in web shaders, for instance, is really, really difficult.
That's yeah, that's
I
feel it's not even like a what's out there, but it's like how would you begin to tackle that problem? Like how would you test, you know what I mean?
Other than like just really good unit tests, I'm not quite sure. I worked on a WebGL project last year where we just made sure we unit tested everything, made sure that all the right calls to the WebGL API were being called, and other than that, like it's a little bit finicky, I think.
Yeah, I guess kind of like CSS testing. It's all when you mix visual with like the math, it just is very like overwhelming. But as I see these technologies and all these libraries coming out really quickly to do WebGL in the browser, I imagine there'll be more like testing suites and stuff that'll come out, or you all should build them so I don't have to, please. What cool things do you see being done with WebGL that people should check out? I mean, besides your stuff, and I've seen links to your demos being posted on Twitter, so if you want to see more of those, you can check that out.
There's a lot of, for instance, games. There's that conversation before, like there's people building like pretty rich games in the browser, which, WebGL is now on 2.0, so it supports higher precision. So graphics are just like a bit clearer than 1.0. I worked on a project that was like it was like a way to learn martial arts. So like there was motion capture data and like the models from motion capture data rendered in Maya, and we kind of had to take those files, turn it into something that can be rendered with WebGL, and like created controls. So we just rotated the camera around to like different parts depending on what the user wanted to like look at and focus on. I mean, Mapbox, and there's another company called Mapzen, and it's another mapping library. They are also creating really, really cool maps with WebGL, and because like they're just kind of doing stuff with maps in the browser and visualizing data with maps in the browser that couldn't be done years ago.
Yeah, that's really cool. That martial arts thing sounds super awesome. I think like one of the earlier like well-known or mainstream WebGL things, I think like NASA did like a Mars rover simulator to like celebrate the Mars rover happening, and like you can pretend that you're the rover and control. It's like not the actual rover on Mars because that would be bananas, but it's like cool to like. There's one thing like telling a story in a game, but actually like allowing somebody to be a part of something. Someone had once told me that like conferences are really cool and there's a lot of conferences to go to, but there are people who have some sort of disability that cannot travel to like all those things. So I imagine like in a few years there being like these fully immersive like simulators where like you're on TV screen like it's as if you're at the conference. Because to be honest, live streams are like pretty crappy, and I see WebGL moving at a faster pace than video conferencing is doing. I think it's on purpose. I think it's a conspiracy, and I think that somebody should look into that immediately, by the way.
Also, Chrome Experiments, they've been doing really cool it's a collection or a curated list of really, really cool WebGL projects. And there's projects like going back into the earliest days of like WebGL support on Chrome.
That's cool. It's cool to see this moving so fast to the web. Like we used to be catching up with like JVM-based languages, and now I think like Java just came out like last year with something that's WebGL-like. So it's like they're catching up to us, and it's like haha. But thank you so much. This is really cool. Thank you very much.
Thank you.